All right, anyway, everyone, thanks for coming. Yeah, Elliot is the chair of my committee. The other committee members are Jan Vassell and Tyler Sesko. And then on Zoom, we have Dan Goldman from Georgia Tech. All right, so my talk is called Leveraging Compliance and Anisotropy to Address Robotic Challenges. So to begin with, we'll start with a general introduction to robotics. So, how do we imagine robots? Everybody right now, think of a robot in your head. And I'm sure some of you might have thinking of this. This is what I think of as I think of a robot. C-3PO and R2-D2, or maybe even the Terminator. Or maybe some of you think of real robots, something from Boston Dynamics, or even something like a Mars rover. But, have you ever really met a real robot? I don't think any of you met many of these. Very few of us are actual roboticists. However, you've probably seen one of these, a robot vacuum, or a drone, or even a surgical robot. So robots, are around, they are part of our lives, but, where are the rest of the robots? There are lots of robots, but the rest of them are all in factories. This is where most of them are. They're building cars, they're building, Teslas and pretty much anything really, just not where humans are. The other half of the robots are probably, sorting your Amazon order. Again, all these robots are in places where humans don't really interact. So another sort of side of this is that certain tasks are easy for humans, but incredibly difficult for robots. So here's a demo of a task that's actually difficult for a human and also very difficult for a robot, acrobatics. This is a very impressive demo. But, that required a lot of things. That required, a robust frame, powerful actuators, onboard energy source, accurate model of robot limbs, models, positioning, control, sensing, etc., and more. But, if any one of those things goes wrong, the system doesn't quite work. So in this case, same robot, something went wrong, and he crashed. So these are all sort of examples of traditional robots, big metal robots. What you think of a robot is probably this. Their advantages, kind of like what you can see, we can imagine. They're powerful, precise, accurate, repeatable, fast, specialized, perfect for a factory. Some challenges are unstructured environments. This means places where you don't exactly know what's happening, such as, office space, outside, in a park, in a forest. There's also soft things like humans. Big metal robot doesn't interact with humans very well. It can, but it requires very, accurate control. It's all delicate things. Another disadvantage can be cost and safety. So our lab, we sort of ask, is there another way we can do this? And what we do is we look at inspiration from nature. For example, let's say a robot hand, inspired by, let's say, a gecko's hand, human's hand, or even some less conventional things that we don't normally think about, an octopus, its arms, elephant's trunk, or even a vine. So these are some actual examples, like human hand going to a robot hand, gecko feet going to a gecko-inspired robot that can climb like a gecko, octopus going to, a soft octopus, as well as, elephant trunk, inspiring elephant trunk type manipulators. So these are sort of all what we call sort of soft robots. A few other examples are stuff like origami robots, little robots that can actually like fold up like origami, as well as growing robots. We do a lot of these in our lab. I'll show you some more later. As well as artificial muscles, kind of inspired by the way human muscles work. They shorten, as well as, little micro flying robots inspired by insects, or even grippers. This is a soft gripper grabbing, a crab. It's something that would, difficult to do with a strong robot arm, but in this case, all you have to do is inflate it and it grabs it. So, soft robots, the key to their success is that they intentionally use compliance in terms of their materials or geometry. So the advantage of this is a passive adaptation, shape change, safety, simple components, low cost. But, conversely, all of these have disadvantages, including, they're difficult to model and control. They often struggle with untethered power, and they have poor accuracy, precision, and strength. Sort of, opposite of the rigid robot in the factory. Is this useful? Well, it turns out, compliance is pretty useful in the real world. An example that Elliot and Charlie actually came up with is the tire. We went from hard wooden or metal wheels to soft inflatable tires. It's probably the most successful soft device that we can think of. Another little thing I thought was fun is that there actually are some examples of soft robot in the media. We don't really think about it. But, for example, the Iron Giant, large metal robot, and more recently, the inflatable Baymax. Or for example, the Terminator series, even the first one is a big metal one. The second one is a shape-changing one, example of shape-changing. And even from Spider-Man, like Doc Ock, originally he has these metal arms. In the animated version, she has soft arms, actually. Anyway, now I get back to my talk, leveraging compliance and anisotropy to address robotic challenges. So I sort of, introduce you to robotics and compliance. Now, anisotropy, I'll sort of break down what this means. The first part is an, as in not, iso as in the same, and tropos, which means turn, or sort of direction. So it means not the same in each direction. So it basically means the physical properties are dependent on direction. So sort of some examples of isotropic, meaning same in every direction, is like a metal. Steel, you work it, doesn't matter which way you pull it, it's all the same properties pretty much. Same with plastics, a bottle, doesn't matter which way you're pulling on it. The plastic itself has the same material and mechanical properties. Anisotropy or anisotropic materials are something like wood. If you're pulling with the grain or against it, it'll be slightly different. Or a composite laminate, different directions you're pulling on it has slightly different properties. Why this is even relevant is because soft robots intentionally incorporate compliance. We think of the rigid robots. The whole idea is you want to avoid any material deformation. You want your robot to be exactly where you think it is. And that's perfect for building a car. Soft robots are kind of the opposite. You rely on material deformation. That's how you can sort of passively, shape change to grab things, et cetera. So now we kind of get to my work. So my projects are kind of in 3 different themes, call it transmissions, actuators, and burrowers. So the first project is this transmission using a Gecko-inspired adhesive instead of gear teeth. The next one was a tri-stable gripper. You can kind of passively do either a pinch or a wrap grasp. Another one is a soft pneumatic muscle, a camera mount and retraction device for a growing robot, a burrowing robot using fluidization, what kind of blows air at the tip, as well as growing. And finally, some self-anchoring devices inspired by plant root growth. So for the sake of time, I'm going to focus on these 4. So the CVT, muscle, burrowing robot, and self-anchoring. So first we'll start with the CVT, which I'll explain what that means. This project was called a low-cost, continuously variable strain wave transmission using Gecko-inspired adhesives. So I'll explain what each of those are. The whole motivation with this was working with Honda, for example, Asimo, the robot. In each of its joints, or at least some of them, it uses both a continuously variable transmission, or CVT. This, can continuously change its gear ratio. Instead of like your bike where it goes like, 1 through 9, it can do anything in between 1 and 9. In addition, they add a strain wave transmission, which is a very high gear reduction transmission. I'll explain on the next slide. So strain wave transmission is composed of 3 parts. We have a rigid outer spline in black, a flex spline in red, and a strain wave generator, the thing in the middle. So this animation on the right kind of shows it. As the strain wave generator spins, it moves the flex spline relative to the outer spline 1 gear tooth at a time per rotation. So you get incredibly high gear reductions, like 200 to 1 in a single stage. But we want this to be a CVT, meaning continuously variable. So if I change the number of teeth, it'll discretely change the gear ratio. So instead of changing the number of teeth, we want to change the length of one of those components. So to do that, we actually sort of took this strain wave transmission idea and sort of turned it inside out. So now we have a fixed cylinder with a strain wave generator kind of orbiting around it and a flexible belt. So each time the wave generator spins, it'll move the belt a small amount relative to the cylinder. And I'll show some videos of this, it'll make more sense in a second. The CVT mechanism, again, that drum in the middle, it is what is changing shape. So this video shows here, basically as these 2 parts actuate and come together, it expands the diameter of this cylinder in the middle. So when it's small like that, its gear ratio is 8.5 to 1. And when it was, puffed up, it was 200 to 1. Again, I kind of mentioned the CVT can't use any gear teeth. Again, I can't discretely change the number of teeth. So instead, we're using a frictional surface. Basically, we get rid of all the teeth. Now we just use friction instead. So we add a Gecko adhesive here, which I'll explain next, which will help increase friction. But a cool thing about the Gecko adhesive is it's not like glue. You can stick really well in shear, but then it's very easy to remove. So this Gecko adhesive was developed by many people, but this version was from Elliot during his PhD. So the geckos, they can climb up any wall, pretty much any surface. And the way it works is they have these small micro features that when they conform against the surface, they lay so close to it, basically, that the van der Waals adhesion is enough for them to stick. So now they can stick in shear, but it can just lift straight off with almost no effort, kind of like this video is showing. So this worked on a climbing robot as well as human climbing. So that's actually Elliot on the right, using pads of the Gecko adhesive to climb a glass wall. So sort of putting these together into our prototype, it's kind of shown here. Bunch of parts to it. This video will show how it works. So this is the part of the CVT. Note there's this yellow marker on the belt, so kind of watch that as it spins. So here we're seeing the spinning wave generator spinning, and you'll notice the line on the belt moving along. Now I start expanding the inner part to change the gear ratio, and you can see the wave generator is spinning the same speed, but the belt is going slower and slower and slower. Now we're at a gear ratio of like 90:1. Then the drum will contract again, and we will go back to a faster speed. Like that. So the idea is here, we know we have both the CVT and the high gear reduction in one device. The gear ratio is kind of hard to work with because this, exponential part, turns out the gear ratio is really simple. It's just ratio of the belt length to drum length. Some other cool parts here. This ply, you don't really need to know much about it, except that adding the dry adhesive, which is the Gecko adhesive, really bumps up the amount of torque we can handle. We looked at the efficiency. It's okay. Especially, for this really crude prototype, it's actually pretty good. Sort of combining these together, we put into a little robot arm. So you can see it's spinning up there and it's lifting a bottle. You notice it's kind of wobbly. It's because it's not quite symmetric. I kind of paused the project here, but then my collaborator Susumu sort of has been continuing this project at Honda. And this was a version he had where he, really miniaturized it, made it a little bit more effective. So that's the CVT. I'll move on to the actuator now. And again, at the end, we have some time for questions. So this muscle, we call it a simple, low hysteresis, foldable fabric pneumatic artificial muscle. The motivation here is that, soft robots need soft actuators. So, there's a whole bunch of different types of soft actuators. I'll just show a few examples. One is the McKibben muscle. I'll explain more about that in a second because this one's really close to my device. Another one is a pouch motor. This one was literally like a bunch of little potato chip bags stuck together. When they puff up, they inflate, but they also shorten. Another version is a piano hazel actuator. It's kind of similar to the pouch motor, except instead of being inflated with air pressure, it actually is using electrostatic forces between two little metal films to squeeze together and sort of make a similar effect. These, at least the pneumatic ones, pneumatic means inflating with air. They're called artificial muscles because they're kind of like your arm muscles where, it inflates, expands radially, and contracts lengthwise. It's not like a pusher or something. Your muscles don't push, they pull. So the McKibben muscle, which is that video I was just showing, is really simple. It was invented like in the 50s. It's probably the first soft actuator ever. It's just a latex tube with a braided sleeve around it. And when that latex tube expands, the sleeve will actually shorten. Just sort of based on the pattern of the weave, it just turns out instead of going lengthwise, its maximum volume configuration is to shorten. However, one disadvantage is it has poor hysteresis due to friction. Hysteresis means basically when I extend and contract, there's some energy and friction losses there, such that you're sort of losing a lot of energy along the way. So that's kind of the key there that we're looking at. My version, functionally is pretty much the same, except all it is one airtight fabric tube. And so it works the same way. Basically, you'll notice here our fibers in the tube, this is really the key, are oriented at 45 degrees to its length, just like the braid. But again, it's just one airtight tube. So that means we don't have the latex bladder, we don't have the rigid braid, which is the tube. Turns out it was actually pretty easy to make. It's just, you cut a tube along this 45 degree, and you kind of roll it, into a tube and glue it together. So here's it working. We have it here hanging with a weight. And when I inflate it, it'll expand radially and contract lengthwise. In this case, this is how you do work. You're lifting a weight like that. Again, here it's just all it is that bias cut fabric tube. That's kind of the key here, because we are using soft robots. We want our actuators to be as soft as possible. Yeah, that's kind of the cool part with the fabric. You can extend along that part. And again, it's literally just a piece of fabric. So when it's not inflated, you can kind of like mess around with it, fold it away in another device. Turns out it's actually a very predictable force and sort of contraction curves. So this plot here, the x-axis is showing your contraction ratio, how much it is shortened. This y-axis is force. Each of these lines is a different pressure. Slightly different version of the plot. Turns out it's really easy to model with the sort of theoretical McKibben muscle equation, which actually doesn't work that well for McKibben muscles because they have a lot of frictional losses. Turns out it actually models ours pretty well. So the dashed lines kind of show the model versus our experiment. One thing to note here that's pretty cool, we have really low hysteresis. Kind of what I mean by that is each of these curves is actually in an inflation and contraction cycle. It's 3 of them. For most devices, these curves, it takes that much force to, go one way and less to go the other way. So that difference is your loss. These ones are almost on top of each other, such that our hysteresis is basically 0. And again, the loss in the McKibben muscle is pretty much due to friction between the parts. In this case, there's only one part, so there's no friction. The advantage of no hysteresis is that we have open loop sort of repeatability. What's going on here is I'm inflating the muscles to different set pressures, and it always goes to the same spot. And if there's frictional losses, that drag, would make it not quite go back to the same spot each time. This one, it goes back to the exact same spot. Another cool part here compared to other soft actuators that is incredibly fast. Again, all it is that one simple tube with very little friction. So you inflate it, it contracts very fast. So some of our other projects, we're using this to drive, very hot, fast, dynamic robots. We actually looked at the sort of its frequency response. In this case, the blue line is my device I just showed. The red one is this series pouch motor, which is kind of that potato chip one where we have a whole big series of potato chip bags. That was kind of our old version of the muscle. Once we realized this was better, we moved on to this. Here is, basically, as we increase in frequency, the actuation is still the same length versus the other one starts to slow down. Here's some cool applications. On the left, this is one of our growing devices. And so as it grows, we have the muscles on left and right. It can steer around. On the right is a little deployable arm, basically just, a little flap with 2 antagonistic muscles. They can inflate to move it around, but you can fold it away because again, it's just a piece of fabric. When it deflates, it folds away. Anyway, that was the muscle. Now I'll get to the next topic, which is sort of what I spent most of my PhD on, which is this burrowing robot. This project was called Controlling Subterranean Forces Enables a Fast, Steerable, Burrowing Soft Robot. So the motivation here is that robots have conquered many environments, but why not burrowing? The answer here is pretty much due to all the high resistive forces. If you think about it, Usain Bolt is an incredibly fast runner through air. Michael Phelps is a very fast swimmer through water, but it takes us forever to, dig through dirt or sand. There's just significantly higher forces. This plot here shows the relative forces, of something moving through sand, air, and water. And you can notice the one in sand, just orders of magnitude higher forces. The other key here is that actually a symmetric object moving through sand actually experiences lift. There's forces pushing it up. The reason for that is basically, it takes more force to jam sand down than it is to just push it up and out of the way. I'll get back to that later. Conventional methods, include something like drilling or excavation. But the whole idea we were going to look at is, is there a way we can reduce the force instead of directly combating it? So the methods we had identified were tip extension, granular fluidization, and asymmetry. So the first one, tip extension, just like a plant, by growing, there's actually no relative motion really between your device and the environment. Unlike a snake where the whole body is sliding, the plant is extending from its tip. So you can see, it leaves the leaves behind. They aren't being dragged with it. The second key is granular fluidization. What this means is basically as a fluid, air, water is passing through something, a granular media like sand, it starts to behave like a fluid. So this octopus is basically pumping water into the sand to fluidize it. Now it can easily just kind of shoop right there into the sand. It's turned that rigid sand into a quicksand kind of. It's not actually quicksand, but that's kind of the idea. Last principle is geometric asymmetry. This is a cool video from Dan's lab looking at it's called a sandfish lizard. Basically, it really quickly can burrow into the sand to escape predators. So here it is, burrowing right into the sand. And so some key about this guy that they identified is the shape of its nose. You notice it has a very wedge-shaped nose. It turns out that the shape of its nose has a very strong effect on how well something can burrow. This plot, you don't really need to know much about it, except that it's showing basically this upward wedge. You try to push to the sand, it'll go up. The downward wedge will go down. The cool part is that a symmetric shape will actually also go up. Again, it's easier to push sand up and out of the way than it is to compact it down. So sort of these different principles, tip extension is eliminating skin drag, granular fluidization reduces the soil strength, and asymmetry counters lift forces. So, we kind of looked at all these things experimentally. First, we looked at tip extension versus intrusion. Intrusion just means like pushing. So here we have a big box of sand. We both push a rod into it as well as grow a device through it. I'll explain how the growth works later. But you'll notice basically growing force is about the same along the way, whereas intrusion, the longer you are, the more and more friction there is. Fluidization, we looked at in vertical burrowing. Each of these little devices is dispersing a certain amount of air, left to right, more of it. You can see it's sort of fluidizing that sand. And these are results there. This axis here on the X is intrusion depth. Y is intrusion force. Each of these is a different amount of air we're blowing. Basically, the more air you blow, basically you can get to the point where it takes almost no force at all to go into the ground, up until you get to a point where basically the pressure of your air can't counter the strength of the sand anymore. But the cool part there is basically you can now burrow with no force, essentially. We also looked at this horizontally. So we had a robot arm with air being pointed either forward in the direction of motion, down, or at any angle in between. This plot shows the forces in drag. Basically, it turns out no matter what angle we're being pointed at, you get a decent force reduction. So if we're moving horizontally, blowing air, doesn't really matter which way you blow it, reduces the force. The difference in these plots is just the depth of our device. The other perhaps more interesting result is that this fluidization jet can reduce lift. So again, this x-axis here is the angle that we're blowing the air at. This is the drag. So it turns out, or it's not drag, this one should say lift. But basically, if we're blowing air in line with motion, it doesn't really affect lift. But as you start to point it down, we actually reduce lift. Kind of the opposite of a helicopter. A helicopter is blowing air down to go up. In our case, if we blow air down, we're reducing the strength of soil below us, sort of counteracting those lift forces. Sort of took all this together to make a robot. So this is the design on the right. We were pleased to be on the cover of Science Robotics. So this device, there's a bunch of different components to it. The blue part is the grower, featuring tip extension. So the way this works is a long airtight tube, sort of turned inside out inside itself. And when we inflate it with air, it sort of unfurls and grows. You'll notice there is a little device riding on the front. That is for the other features. The first one is a forward fluidization air jet, like this. We use that to reduce the strength of the media in front of it to help it burrow. The second principle is a downward directed fluidization jet. That one's more for controlling lift. So by sort of modulating the pressure between the two, we can sort of change the direction. The last one is steering. So we basically added tendons inside this guy. So just like your arm, you contract one of your muscles, it'll turn one way. So here we are, goes this way. Anyway, sort of combining these together, we can achieve horizontal burrowing. This video, for reference, is 1 meter across bed of sand at 2x speed. What you're seeing here is a little mast glued to the head of the robot so we can tell where it is. And the bubbles you're seeing behind it are from that fluidization. A key here is that we have to use this downward airflow to control the lift forces. So with no downward airflow, no matter what, we always end up surfacing. It's really hard to stay horizontal. But with the perfect amount of airflow, we can control or sort of modulate up or down our lift forces. Kind of what the plot on the right shows. If there's too much air, it'll just blast us out of the ground like a jetpack or something. We can also burrow very quickly. So this video on the right, you just watch closely, watch the toothpicks. I'm in the matchsticks. They just move like that. So what's going on? Next will show slow speed. The robot is burrowing really quickly right under the ground. We're not actually trying to control horizontal growth in this case, it's just growing along a wire, but we're kind of just showing using pneumatics, you can go incredibly fast. What we looked at here was sort of the force and how that has changes with rate. Turns out, if you go very fast, there's more and more and more force. Not shown here. In the very slow regime, interestingly, in granular media, friction forces, aren't rate dependent. Using steering, we can add a serpentine path. So I was originally going towards that block. We go right. Now we're going to start turning left, make a little S shape. The robot was coming inside right up there. Then we can also steer in the other directions. This is going down under a cinder block wall, and then come up on the other side. Then I'm just removing the cinder blocks, showing you that it did indeed burrow underground. And then I pull that guy out. For reference, this bin is like 750 pounds of sand. We are sort of fortunate to have this sort of picked up and then got featured in a video on Veritasium. This is his YouTube channel with a sort of famous YouTube science communicator. So that's him, that's Derek. Here he is at my house during COVID. I'm showing him how air fluidization can help with burrowing. So we're there looking at that. So the video, if you want to watch it, called "This Unstoppable Robot Could Save Your Life." And we're proud to show that now it's 32 million views. So a lot of people have seen this stuff. Our Vine robots, our burning robots, different versions. David has a medical version of the device in here. So if you're interested, you can check that guy out. So I get to my last talk or last section. This is sort of what I've been doing the last couple of years. All the stuff I've actually shown you so far, it was actually from like 2000 or 2021 and previous. Since then, I've kind of worked on a lot of sort of not quite published stuff yet. So this last section, this talk is sort of called Plant Root Inspired Self-Anchoring and Reduced Gravity. So what we're doing here is that, again, we're looking at burrowing. The motivation is that burrowing deeper requires more force. So for example, you want to put a fence post or a sign in the ground, you need a big drill like this on the back of a truck. You want to dig a well, you need an even bigger truck. You want to dig an oil well, you need a much, much bigger one. Basically, the deeper you're going, the more and more reaction force you need. You need something to be able to push your drill into the ground. But plants, don't require any external reaction force. Starts out of the seed, creates a big root structure. Nobody needed to push on it. It just goes. So we were wondering, how can plants, make these giant root structures like this? We don't often see them, but the root structures are often, as big as the tree itself. These particular ones are root structures that do go very deep. Others might stay more shallow to collect, surface moisture. So we're sort of looking at mechanical features of roots. Some of them that we identified in terms of anchoring were tip extension, root hairs, branching, and radial growth. Again, we're looking at mechanical anchoring. Roots do a lot of different things. Other parts are nutrients, water, etc. Again, the first principle is tip extension. Like I mentioned earlier, the key here is that there's no sliding against the environment. This means that for a root, no matter where it goes, it's not like it has to drag its whole root structure with it. It's just growing. The key here for anchoring is that now your skin friction, instead of countering your movement, can be used to counter the resistive forces at the tip. I'll kind of show that a little later. The second cool feature are root hairs. This, I think, this particular video I'm about to show really inspired this work. So this is a maize seed, kind of like corn. growing into the ground. It's a little seedling. This is its first root. As it starts to grow, it's starting growing. It's kind of hard to see, but the top half there, it starts sprouting little root hairs that they pop out and they grab onto the soil around it. And now it can keep going deeper and deeper. This video on the right is a mutant type genetically modified to have no root hairs. So as it's growing, no hairs pop out. And so instead, it just keeps growing, but instead of going deeper, it pushes its own seed out of the ground. So the results, at the end are kind of showed here. This wild type, as it grows, eventually its root hairs hold on to the soil and now it goes deeper. Versus the mutant can't go any deeper. Instead, it pushes itself out. Another cool effect is branching. So this is a cool paper where they grabbed a young plum tree, only a few years old. That tree there, it's maybe 2 or 3 inches in diameter. Took almost 2 tons of force to pull it out of the ground. Again, you're not just pulling the tree out, you have to pull all that soil around it. It has to come with it. The last effect is radial growth. This one, it's a little harder, at least in a tree, because it's growing so slowly to see the effect of it. But we think, things going into the ground and expanding, kind of like this simulation from this paper is showing, as they expand, they compress the soil around it, they increase its loading. Now that soil, is sort of stronger. So taking these principles together, we get to self-anchoring. Basically, what this means is that when there's friction forces or matching your resistive forces, your self-anchor. So sort of illustrate this, looking at intrusion. Let's say you're at the beach, you have an umbrella, you're sticking it in the ground. That's your force at the top, pushing it in. What you must counter is this resistive force at the bottom from the soil, as well as some friction. The deeper you go, the more resistive force there is, and the more friction there is. So you need to push even harder. So that's why you step on a shovel, you're only going to sink so far and you won't go forever, because eventually these forces will counter your weight. So it requires a high reaction force base to push it. A tip extension, like the plant, is a little different. It's starting out there, it has to counter the same resistive force, but now it's sort of friction or anchoring force is in the opposite direction. It's countering that resistive force at the tip, meaning once it's grown far enough, those sort of anchoring frictional forces actually can match or exceed the resistive force of the base. So notice that one takes no reaction force to push it in. That's how that seed was growing. So basically your frictional anchoring forces are countering your resistive forces, enabling self-anchoring. So we've been able to implement some of these features. This video shows a device that one of my undergrads helped me make, where it's our growing device, and we've attached these little sort of rubber hairs to it. So as it grows, these little hairs, inspired by the plant, just pop out. So here's a version of it growing into sand, growing into our little sand bed. You can see them, it's kind of popped out. And then as I pull it out of the ground, they kind of, they've grabbed all that sand around it. So they actually work for self-anchoring. So here's a demo. This is the same type of robot, just a little smaller, and growing into a bed of lunar regolith simulant. Here it's grown maybe an inch in, and actually just let go of it. And you'll see that string attached to its tail starts to, grow through as it's growing. Then it's kind of hard to see again, because it's just in the ground, but I can now pull it out, and it actually takes a non-negligible amount of force. There I go. It has actually grown all the way to the bottom of the sand bucket. You can see those little hairs there have grabbed onto the sand. Without those hairs, there's not much anchoring force. It'll just, I'll have to hold it the whole time. This plot kind of illustrates the 2 different features. So x-axis is just time as we had some things going in and out of the sand. Y-axis is force. This blue one, intrusion, is like that rigid rod I showed earlier. As we go deeper, it requires more and more and more and more and more force. So we stop, and when we pull it out, it takes almost no force to pull it out, just a smooth rod. Meanwhile, the grower, this force here, it's a rigid setup. It's a little different from that. It doesn't really represent much, but basically it takes a lot of force to pull it out, more force than it did to push it in, meaning it was self-anchored. I don't actually have to hold on to it like I showed in the video. Once it gets going, I can just let go and I'll keep growing all the way to the bottom. In the future, we kind of want to combine these different principles. So for example, we start out with a small weight. We grow, several different branches with hairs. They grow all the way to the bottom. Then they expand radially for maximum anchoring. So a revision here is self-anchoring on the moon. So the challenge here is that, let's say you have a rover, it can only provide 1/6 the reaction force due to the reduced gravity. So our solution is maybe robotic self-anchoring. Now you can now enable sampling and sensor placement. So let's say this rover, it's here. We want to do some soil experiments. The rover is very light, it's a very small rover. Now it only has 1/6 the force. So to go deeper, you would instead deploy these anchors. Now you can do your soil experiments. Or the growers themselves could be the experiments. So we have a really cool, unique opportunity with a Blue Origin 1/6 gravity suborbital spaceflight. So our device will be riding on a Blue Origin rocket. The way it works, the rocket goes up. There's a space capsule at the top that separates. It flies through space for a little bit, and then it comes down. But this is the thing that Jeff Bezos is famous for flying on, with some other people. But the other half of Blue Origin's work is experimental flights like this. What's unique about ours is once that spacecraft is up there, it actually start rotating to induce artificial gravity inside of it. So now every experiment inside the spacecraft will experience 1/6 g as if it's on the moon. So to that end, starting out as a capstone senior student project, with the help of many, many undergrad students, we've developed this automated anchoring experiment. Its actions will be to repeatedly reset a tank of lunar regolith simulant. So that's this cylinder here. It's full of basically fake moon dust. Then into it will be 2 tests. We want to compare the force basically on that rigid intruder versus my growing anchor, kind of like the plot I just showed. Kind of hard to see, but this part's the regolith. These 2 guys here are the 2 experiments. So shown here, the frame, regolith container, pneumatic system, penetrometer, tip extending device, electronics, secondary containment, a bunch of other stuff. So this is a little self-contained growing device for the anchor, kind of like a lot of the other videos I showed, but this version is attached to a little spool you can see in the right. So as that rotates, it lets the thing grow, and then it can spin the other way to retract it, so I can go again. This one doesn't have the hairs on it yet, but eventually it will.
What are the hairs going to be?
So the hairs right now we've been making out of TPU, kind of like that video I showed earlier where they're unfurling as it grows. So our electronics, all of our electronics are using off-the-shelf boards put together on our own custom PCB with connectors, and the whole thing is potted. So you can see it's kind of shiny. It's basically in a resin to hold it in place to resist vibration. So we actually successfully went through vibration testing at a aircraft testing place. So the video on the right is showing its internal camera. You kind of see some stuff flapping around. Basically, these vibrations are to simulate the rocket launch to show that our device can withstand the acceleration of it. So turned out fine. Another test we did was EMI testing, so electromagnetic interference. We basically need to prove our device won't, bother other people's experiments or interrupt, the rocket signal. Turns out we didn't pass this test, so we'll have to come back to it later in the summer. These pictures here are showing the device. It's just running. There's a bunch of fancy antennas that detect emissions from it. Some other ongoing works are related to these burrowing and anchoring projects. This one project I'm working on right now with some students is looking at failure prediction and distributed loading. The idea is, kind of with a rover or any other system, we want to have, a bunch of anchors, and we want to distribute the force amongst them the best way possible. The picture on the right shows a little sandbox. We have 3 little anchors in it. They're each being pulled out by a little spool. And here's the forces on them. We're pulling, then each of them at a slightly different point, yields and fails, and it comes out of the ground. The key here is that each of those points, we can actually sort of predict when it's about to come. So this plot here, the bluer line is showing the actual force. The orange one is showing the first derivative. So basically just the change in slope, or no, it is just the slope, basically the change in force. What we do is we look at that bottom point there, and when that when that derivative is starting to decrease again, we can now stop there because we're about to hit the peak. So this is an example using real-time control. Again, the bottom plot is showing the derivative. we've identified, hey, our derivative is about to decrease. So we stop, and now the device actually just stops pretty much at its peak. Then we demonstrate, if you kept pulling, its force would suddenly drop off. So you can now tension up all your anchors right before they're about to hit their peak and stop pulling harder. Another work we're really excited about is looking at sort of physics of soft branching structures. So this is a really cool, unique simulation my collaborator Dennis, or Georgia Tech, has been working on, where he can grow into basically a granular media. We can simulate growth with branches. So the next step, we will be comparing that to basically experimental results. So I have this version of my grower on the right, which also has branches. So there we are, we're growing with branches. Again, we will next be comparing that to the simulation results. We're not entirely sure what we're going to find here. We're again trying to look at the physics of the system, both experimentally and simulation-wise. These are things nobody's ever done, actually, looking at sort of branching structures. Because one, you can't deploy a branch structure without growing, really, like into the media. That's kind of the work I've shown here. The publications I just showed. This first one is the CVT, second one is the muscle. These last two are both on the burrowing. One is a conference paper, and then one is our journal paper. I have a bunch of other publications, so some journal papers, more conference papers, more conference papers. So in all, our lab is very collaborative, as Elliot says. That's how I've come up with 18 papers now in the last 6 years. Pretty crazy. Cool thing with my work is we actually have some patents too. So we just got issued our first patent on burrowing with basically emission. So that's the patent for basically blowing air at the tip of the robot. These other two applications, which we're submitting as full patents this year, are on the self-anchoring that I showed at the end, as well as using growing to deploy subsurface sensors. Then we got a few other provisional patent applications, which we'll see if they, end up being submitted or what happens with them. Yeah, about right on time. But so acknowledgments, this work would not have been possible without the support of many people, as you've already seen. First and foremost, Elliot, my advisor, couldn't ask for a better advisor. Elliot's been awesome, great role model, great mentor. It's him and his dog Pema. And there he is at the top of that mountain that he showed earlier. Once he got there first, so he got to use the broken telescope to look around. The rest of my lab is another backpacking trip. So David, Charlie, Matt, Anna, and me. We got Luke, and then also Drew, who was a master's student in the first few years. My work is, pretty cool. I've been able to work with tons of undergrad students who have been, made very meaningful contributions. Some highlights, there's many just in alphabetical order: Sean, William, Nick, Aaron, Jonathan, and Sichung, as well as the entire Trilogy capstone team. So that was another 11 students who started out on my that anchoring space project. My other advisor, Dan Goldman, who's on the call here, hopefully still, he's been a very great collaborator. He's a physics professor at Georgia Tech. I think definitely what I've learned from him is sort of, Dan likes to ask bigger questions. Elliot and I often, approach things as an engineer, and he's like, sure, but what more can you do? What more can we discover here? So that has been very helpful, sort of, I think, for both Elliot and I to grow our lab. I also have many external collaborators from many different places. Two key people here. One is Andy from Georgia Tech. He helped a lot with the first burrowing paper. He did basically all the physics experiments. He sort of came up with a lot of that. He's a granular physicist, as well as Dennis, who I've been working with also at Georgia Tech on all of the anchoring projects. I think some other people I'll point out here is the ME front office, Julie, Amanda, and Milicia, especially because I've submitted over 420 purchase orders over the time here, which they've all, helped out. Our style of work in our lab, if any of you have seen it, would not be possible without all of the random stuff we're ordering. Again, my family, some of them are here today, especially my family for letting me do a lot of my work in my backyard during COVID. So pretty much all of the work in that science robotics paper was done in my backyard or in the basement during COVID. So you saw that box earlier that was built in the backyard. And finally, some collaborators, funders, a lot of it was from NASA. I have some advisors there, as well as NSF, Honda, Lockheed, and UCSB. So thank you, everyone.
Yeah, so we'll take some questions from not the committee and just we'll hold our questions for the closed session, but anyone else, feel free to ask them questions.
Yeah, then if you guys can, anyone on Zoom, feel free to write in your questions and then maybe.
Yeah, I can
maybe you can
monitor
look for them. Yeah.
So on your first of all, great presentation, very enjoyable, it's been great seeing you progress from, you know, the guy who FaceTimed me when I was thinking about joining the lab to the point you're now you're well on your way to becoming a professor. But you know, I guess the question that came up for me during this presentation was around the FPAM. And, you know, presumably a reduction in hysteresis probably also corresponds to an increase in, you know, cycle life or, you know, performance life.
Yeah.
Did you measure that at all or experiment with how, you know, I guess design insight corresponds not just to, you know, these improvements in function, but also these improvements in, you know.
Yeah, so for people online, Dave is asking a question about the FPAM, the muscle, and what its lifetime is. And so again, as you mentioned, we have reduced hysteresis. So I actually did test its lifetime. I guess I didn't put in here. We tested up to 10,000 cycles, or 10 or 100,000 cycles, and there was no change in performance over that period. So, you know, it is fairly robust to that. However, because it is just made of this fabric, it is somewhat delicate to like pinprick leaks or tears. So it's very repeatable, you know, just sitting there going forever. But, you know, if you're driving it, you know, on a robot, you know, through dirty environments, through rocks and sand, it'll eventually get little holes and leaks. So its performance will degrade, you know, but yes, that's one thing. So one thing with the performance, this material that we've chosen is one that, you know, has a very strong bias where basically if we pull it in one axis, it will stretch, whereas the other it won't. So if you went to a thicker, more robust material, it might not work the same way. So it works well for this stuff, but, you know, perhaps is not suitable for your, you know, industrial applications.
How does that cycle time correspond to compared to muscle?
How does it compare to McKibben? I'm not sure. I looked at some McKibbens. I think people have designed some that work really well for a very long time, but it's really crude ones like this. You know, ours literally just tube. I tie a knot in one end and attach it to a fitting on the other. We're probably similar or worse, because there is that friction between the rubber and stuff that might degrade faster. So comparable, I'd say.
Since you presented this kind of a big range of projects,
yeah,
how has your approach to solving problems changed? You know, going from like CBT to the recent burrowing work.
Yeah, that's a good question. Like, how's my approach to research and problem solving changed from the beginning? Yeah, it's a really good question. I think a big thing, I mean, they're all similar. I think one thing that Elliot taught me is sort of stressing the importance of like a critical function prototype. Basically, you know, what is the most important part? You know, what part that if it doesn't work, the whole system doesn't work. Can we try that and test that earlier and first? That was one of the first things I learned. Then I think a lot of that work on the burrowing with Dan was like, we don't quite understand it. We're just beating it. You know, as an engineer, he's like, all right, you got to step back and like, can we understand the physics? You know, what is actually happening here? So it took us a while to figure out the lift force in the granular media. That took forever for us to understand. Turned out burrowing vertically is really easy. Going horizontal was actually way more difficult than we thought. And it was because we didn't quite understand, you know, the physics of what was going on. And I think sort of later, some of the stuff I've learned with the spacecraft project, something there is one, designing things to be very reliable is very difficult, as well as designing things for very strict regulations and environment. You know, like we have to conform to like military spec vibration and EMI. That is a lot of work. As well as a lot of electronics, that took me a lot longer. You know, I had to learn a lot about microcontrollers and like embedded hardware and stuff. I guess like, how does my approach change there? I guess, I don't know, trying to talk to more experts and things like that would have been helpful, because I've since, you know, met some people when I was at NASA who like, oh yeah, just use this and that. And I was like, oh, I should have known that a year ago. You know, that would have helped, because, you know, our lab, you know, we're not experts in everything. So yeah, I think going to talk to experts is one of the big things I've learned. You're not going to be an expert in everything, but somebody else is. So try to find them. Yeah.
Thank you.
So I have a question. So as, let's say your burrowing robot gets really deep in the soil, in the circuit, it's a really high pressure,
Mhm.
so like, let's say you're a really dead soil. Have you considered alternative methods to either like inflate or fill your burrowing robot? And if so, what are those things you can do?
Yeah, it's a good question of like, as we're going deeper with burrowing, we get to higher pressures, higher strengths. I think a couple of things there. One thought is that all the things I showed in the burrowing slide, like growing, fluidizing, asymmetry, those could be worked in with another device. Like you could have a growing body, but literally a drill on the front to help your way through. Our thing can't go through a rock or anything. You need a drill, but adding a growing drill, might be helpful. For the anchoring one, the idea there is, plants don't have to fluidize. Can we just brute force it, kind of grow our way through? And the idea there is that if we can grow at the same pressure as a plant, we should be able to grow to where plants can grow. So we've made versions that go up to like 1,000 PSI, which are inflating hydraulically, but that's kind of the limit there. I think the hardest thing to change is the growth. Our method, at least with that eversion, we haven't quite figured out how to do that, not without some sort of fluid pressure doing it. That seems to be the best way. So I think the key there would be to combine it with force reduction mechanisms, either drilling. The other ones we looked at are like vibration or sonic drilling or ultrasonic cutting, things like that, to instead reduce that force instead of trying to directly go 1-to-1 against it.
You mentioned hydraulic operation. Were there downsides to that approach?
Yeah, so the hydraulic, the advantage with hydraulic is we can go to much higher pressure without risk of things blowing up because there's no stored energy in it because it's incompressible. The only downside is we need to know like a hydraulic pump or something. It's kind of a hassle. It's kind of messy. But besides that, it's probably easier in some cases. Basically, if you're going higher pressure, you pretty much have to go hydraulic. So ours, we just inflated with vegetable oil actually and just did it outside.
There's a related question online, which is there a fundamental limit to how deep you can burrow in your granular media? Is there a depth limit at which fluidization no longer works?
Yeah, is there a depth limit for the fluidization? I think it's more of a strength limit. So if we have a very loose, very low density media, you could go like tens of meters in and still be able to move it. But if you had a very compact, strong, dense media, that limit in terms of strength would happen much sooner. For example, I recently did some tests in either loose state media or compacted. And for the exact same robot in the loose state, it goes at least a meter in. In the soft one, it goes like 5 or 6 centimeters in because the force is the same. I think the limit is more the strength of the media, not so much the depth. I mean, as you go deeper, the strength increases, but it's really the strength. So in what I've actually shown in the medium that I've shown in that sand, it's on the order of a meter. Again, if it was extremely loose or extremely compact, it'd be a little different. But right now it's on the order of a meter or so at these pressures. If we go higher pressure, we can go deeper. If we use some better force reduction mechanisms, we could probably go deeper as well. Yeah.
Fantastic presentation.
Thanks.
My question was about the fluidization.
Mhm.
So you said that to burrow horizontally, you needed some vertical fluidization. Whereas if you go too much, you might just like lift up.
Yep.
So for things like that, have you thought of how do you control the airflow, the actuators?
Yeah, so like the airflow, we're asking about the airflow for horizontal for controlling the lift. So it's a little tricky. In our case, it is kind of open loop. I'm just literally at the back, opening some valves to see what happens. In the future, maybe you could add some sensors at the tip to detect, your orientation and sort of use some more closed loop control to change, how much air you're pointing which direction to change certain things. In our case, we think with blowing the air, you can only ever get to neutral. You can't get negative lift actually. So basically, if you've disappeared the sand, you should have no lift. So that's why our device actually has a little wedge on the front. So it naturally is trying to go down a little bit, but it's not quite enough on its own. So it needs some of that fluidization to reduce the lift. But now we're in the range where if we get just enough, we can go down. If we have a little less air, we'll go up a little bit. If we have no air, we'll just pop right out.
One more online. So from Yasmin, is there an ideal ratio between main body and side root? What is the growth
Yeah, for anchoring for main body to side rig. That's a good question. So we haven't really explored that part yet so much. I think there's a couple of things there. One, we do hypothesize that it is better to have many smaller roots than one big one. The idea here is, let's say my robot can only inflate to 100 psi. That basically determines how deep it's going to go. So for that depth, we want to minimize its cross-sectional area and maximize its surface area. Basically, its surface area is kind of proportional to how much anchoring it has. More surface area, more hairs, more et cetera. The area at the front is like how much force you need to be countering your movement. So instead of one big one, it'd be better to have many smaller ones. For the branches, we have looked at some simulations a little bit. It turns out one thing is there is some optimal spacing. If you have too many, they're too close together, it's as if you have no branches. It's just one big device. If they're too far apart, there's not that many. You could have had more. There's probably some like interaction effects within the media with them where they can more constructively sort of interfere with each other. That would help. We haven't quite understood that yet. That's kind of what we're going towards. Practically for the branches with our inflating device, if the branches that are inflating are too small, they don't grow very well. They need a lot of pressure to pop out. So for our device, practically, they need to be a similar diameter as the main body. But yeah, there's a lot of things to explore there. Kind of our idea is that if we can show that our simulation matches experimentally, then in the simulation, we could start varying things that are harder to vary experimentally.
Other questions? So maybe I'll conclude with Susan's comment that our Honda collaborator who says perfect presentation. So with that,
Thank you, Susan.
Okay, so we'll go ahead now and do the closed session. So if anyone else wants to move on out, grab a muffin. I think the muffins are not even been open, so please grab a muffin.
Thanks everyone on Zoom.
We will